Okay, so in this problem, we are going to use method of sections. And we want to find BD, CD, and CE. So BD, CD, and CE. We found in the last problem that we had 80 kilonewtons on this side, and we had 40 kilonewtons over here. So we're actually going to work this problem 2 different ways. And again, post-it notes. Post-it notes are your friends. When we do method of sections, we are literally going to cut the truss in roughly half. And so if I look at this left half, I would have 80 kilonewtons plus the 120 applied, and then I would have the 3 members, which I assume in tension. If I cut it in half, I can use the right side and I just have 1 reaction. Okay? So let's look at the left half and then we'll do it by the right half. Again, we should have the same values either way. So it's a good way to practice method of sections is to work your problems twice and work it from both sides. You should end up with the same answers, but it'll also give you some nice practice. So with method of sections, I'm going to come down here and I'm going to draw. And I have something that looks like this. So I have this force at B of 120 kilonewtons. Okay. At A, I have 80 kilonewtons. This is 3 meters. And I can see I have a force pulling and tension here and a force pulling and tension here. These are both going to that same joint. And this is going, so this would be E. This would be D. This whole height here is 4 meters. The slope of this is a 4 to 3. Okay. And this is 3 meters from C to E, and then 3 meters from A to C. Okay. So there are lots of ways to look at this. When I'm using method of sections, I can sum forces X, I can sum forces Y, and I can sum moments. So if I look at summing forces in the X direction, I have 1, 2, plus the X component here. That's 3 unknowns. Not super helpful. I could, however, sum forces in the Y direction, X only, and get this Y component. Okay, so that would give me 1 of my unknowns. Summing moments. I could sum moments about D. Both of these go right through D, so I could calculate this member force. I could sum moments about this joint right here, because this and this both go through here. I could solve for my force in BD. So this is my force in CD, and this is my force in CE. Okay. There's lots of ways that you can sum more moments and forces. You know, we could sum moments about any point on here we wanted. So I'm just going to start with, I'm going to sum forces in the Y direction. Up is positive. And I'm going to start at the left and work my way around. So I have a positive 80 kilonewtons minus 120 kilonewtons. X component, X component. This has a Y component. It's pulling in tension up. So it's going to have a positive Y in terms of equilibrium. So I have plus 4/5 F CD equals 0. And I have 4/5 F CD equals 120 kilonewtons minus 80, which is 40. So I have F CD equals 40 times 5 over 4. And I get 50 kilonewtons. Which is exactly what I got the last time I solved it by method of joints. So we have 50 kilonewtons in tension. Okay? And it makes sense. This is much bigger going down than this is going up, so this has to be kind of going up. So we've used summing forces Y. Now, can I use summing forces X? 1 unknown, 2 unknown. Not so helpful. Positive tension, so there's that solution. So X isn't going to work very well for us. So let's sum moments at D, because if I sum moments through D, it gets rid of this, which has the X and Y components, and it gets rid of an unknown in the X. So we're going to sum our moments about D. equals 0. So here's our point. We're going to start left, work our way around. So we have a negative 80 kilonewtons. Okay, if I'm looking at D, 1, 2, 2 panels, so I have 6 meters, plus 120 kilonewtons. If I look at D, it's just 1 panel over, so 3 meters. And then goes through D, goes through D. We have this unknown force CE, positive rotation plus FCE, and its perpendicular distance up is 4 meters. So I have FCE times 4 equals 80 times 6 minus 120 times 3. So let's pull out our handy dandy calculator. I need to put batteries in here. Okay, and I have 80 times 6, 120 times 3, add those up, 120 divided by 4, and I get that the force in CE is 30 kilonewtons. I got a positive value, tension. Okay, 30 kilonewtons, tension. Now that I know force here, I can come back and we can sum forces in the x direction. And this was in tension, so I have 30 kilonewtons. Okay, this has an x component plus 3/5 times 50. Okay, plus force BD equals 0. So my force BD has to equal negative 30 minus 3/5 times 50, which is also 30, negative 60 kilonewtons, which is 60 kilonewtons in compression. Okay, so member BD is 60 kilonewtons in compression. And that's exactly what we got doing method of joints. So our numbers check out using method of joints. How can we go back and check to make sure that this is correct? Well, let's sum moments about point C. I can sum moments about point C to check. If I'm looking at point C, I have a negative 80 times 3 straight through. I have that force in BD. Okay, that force in BD, which was in compression, so we're pushing back, so I have plus 60 times 4. This goes through that joint, this goes through that joint, so this equals 0, and I have a negative 240 plus a positive 240 equals 0, 0 equals 0, check. Okay, I could also come back and draw this from the other side. And I have 40 kilonewtons as a reaction. When I look over here, I'm pulling. That's my force in dB. It's going towards B. Okay, I have the force down here, force in CE. It is going to C, dot, dot, dot. Okay, I have the force here that's going from D to C, dot, dot, dot. Force DC. My height is 4 meters, and I have a panel that's 3 meters and a panel that's 3 meters. So this would be the right side. This is the left side, and we'll notice that BD and BD, I assume they're both in tension pulling each other. When I put it back together, to the left, to the right, add that in equilibrium, it equals 0. So when I'm looking at my whole picture, I don't see that internal force. Same down here. Force CE, I'm assuming in tension. Force CE, I'm assuming in tension. Depending on whether the right or the left. One is going to the left, one is going to the right. Okay, they have to be the same value. It's the same member. It's 0. So when I look at my overall picture, again, I don't see anything internal. So overall pictures to find reactions, we don't see any of this internal business. Once I cut it, anything I cut, I have to show as a force. It's why I can't just cut the top off Because when I look at just the top, I would have 1, 2, 3, 4, 5 unknowns. Okay? And actually, well, I could find this one. I can't do anything because I have 5 unknowns and I have 3 equations of equilibrium. Okay? If I cut the top off, 1, 2, 3, 4, 5 unknowns, and I just have the 3 equations of equilibrium. That's why you can only cut it through 3 members unless one of them is a 0 member force. Okay?